bosonization of Fermi liquid.
Okay, thanks a lot, Alessandro, and thanks to you and all the organizers for bringing us together in this beautiful place. I've enjoyed this conference a lot so far. So this talk will be about bosonization, but not the type of bosonization one usually discusses in the context of CFTs, and that you probably heard about from Chong Wang. This will be the bosonization of Fermi liquids. So you can think of Fermi liquids and non-Fermi liquids. They're strongly interacting cousins as critical systems in their own right. In fact, they're quite stable critical systems, so they arise in nature quite commonly. But they have much fewer symmetries than CFTs. So this, on one hand, allows for many new possibilities, but it also makes them much harder to study. And so I think even beyond experimental motivation, I think it's a very interesting testing ground for quantum field theory for kind of pushing the frontier of quantum field theory tools to situations where you're very far away from the relativistic vacuum that particle physicists are used to. I'll present our work on building an effective field theory for Fermi liquids, where that we hope will help study these systems and perhaps go beyond Fermi liquids. So let me quickly introduce my wonderful collaborators. Ixuan Du and Umang Mehta are graduate students at the University of Chicago. They're applying this year, so keep your eyes open for them. And Son needs no introduction. Okay, so probably most people here don't think about Fermi liquids on a daily basis, so I'll start with a gentle introduction. The simplest Fermi liquids are just free fermions, what you get when you have a lot of free fermions. So let's say you have a box and you put a fermion in the system, an electron in the system. If it wants to minimize its energy, it's going to occupy the lowest wave vector state, which will look like this. This will be its single particle wave function. And to denote that this state is occupied, I'll put a little dot here at kx and ky equals to pi over L. Now, if I add another electron, ignoring spin, due to Pauli exclusion principle, it's going to have to occupy another state. And so the next lowest wave vector state is going to look maybe like this. And so I'll have this state that's occupied. And if you keep on going and add more and more electrons to your box, you're going to slowly populate all these low wave vector states until you have a lot of them. And I'm going to be interested in thermodynamic limits, where I keep the density finite, but my box size goes to infinity. In which case, I can think of this object here as a smooth object, a Fermi C. So even though we just have free fermions here, it's a pretty unusual system from the perspective of kind of vacuum quantum field theory. In particular, it's very gapless. So you have all these zero frequency, zero energy excitations at finite wave vector, right? You can imagine taking a fermion out here of the Fermi surface and adding it over there. This is a basically zero energy process, but it has a very a large wave vector of order the Fermi wave vector. And in particular, if you look at spectral densities, so for example, the current spectral density, because of this, you'll get this whole continuum, this whole spectral weight at zero frequency and finite wave vector in, for example, the current two-point function. So this is just a contrast with what happens in CFTs. If I have a free CFT, the spectral density would be all localized at omega equals k. If you add interactions, you would start having multi-particle states, and you would have spectral weight over here, but you would never have it at omega smaller than k. So here we really have a very gapless system. And you can think of these gapless excitations as modulations of the Fermi surface, right? If I take a bunch of particles here and put them there, I'm eventually going to change the shape of the Fermi surface. Okay, so there's one important dimensionful quantity in the game, the Fermi wave vector, which is just the size, the radius of the Fermi surface. And so you could hope for an effective description for distances much larger than this than 1 over kf. Okay, and indeed there is an effective description. So if I have a very big system, I can cut it into smaller boxes each of whose size is still much bigger than 1 over kf, so that in each of these boxes I can still define a smooth Fermi surface. Okay, so now so this is an inherently semi-classical picture, but it's allowed thanks to this large dimensionful scale kf. So now the Fermi surface can actually depend on space as well. For example, let's say over here, there can be more electrons moving with momentum to the right, here more electrons with momentum to the left. And if I time evolve this image, inevitably what's going to happen is that they're going to increase the density over here, okay? So there's some continuity relation, which underlies this system, and it's just the collisionless Boltzmann equation. Here, F is the occupation number of particles at position X, this coarse-grained position X, and momentum P. So this was all for free fermions, but Landau's genius step almost a century ago was to realize that interactions don't change this picture too much. There's a right-hand side kind of collision terms that we can now think of as Wilsonian coefficients that are called Landau parameters, but the degree of freedom in interacting Fermi liquids is still essentially the same. So Landau's theory of Fermi liquid is extremely successful. It has a number of applications. Probably the textbook application is helium-3. So helium-3 is an atom that has an odd number of fermions, so it's fermionic. If you cool it, it becomes a Fermi liquid. And it's so you can do a bunch of experiments on it. And a lot of predictions from Landau's theory of Fermi liquids are borne out. So for example, the specific heat is very large at high temperature, which again it comes from the fact that these are very gapless systems. There's a lot of excitations that are ready to be excited. So just to compare to a CFT, by scale invariance in a CFT, the specific heat would go like temperature to the spatial dimension, okay? So at low temperatures, this is much larger. The thing that makes up units is KF. There's also collective excitations that are predicted by Landau's theory of Fermi liquids. You can measure these parameters that I mentioned in helium-3. You can also do out of equilibrium measurements and measure the viscosity, and those all agree with even quantitatively with Landau's theory of Fermi liquids. But the reason condensed matter physicists care about Fermi liquids is that they describe also most metals that we have. So in metals, the fermions that make up the Fermi liquid are charged under ENM. So that allows us to use a bunch of different probes to see them. In particular, we can image the Fermi surface. This is an example. So you see that it's, it has a fewer symmetries. It's not isotropic, but with a few cosmetic changes, Landau's theory of Fermi liquid still applies and gives a bunch of predictions. Let me also mention that there's high energy applications of Fermi liquids. The part of the QCD phase diagram is expected to be in a Fermi liquid phase, which might have implications for astrophysical objects. So Fermi liquids are all over the place, but there's also a reason to want to go beyond Fermi liquids. There's motivation both from experiments and theory. So experiments, there's a growing number of systems that seem to go beyond the Fermi liquid paradigm. They still have a Fermi surface, so we expect them to be, again, these very gapless phases of matter. But a lot of observables don't agree with Fermi liquid predictions. An example is the strange metallic phase of high temperature superconductors. But even if you don't care about experiments, there's a good reason to want to go beyond Fermi liquids, just because you can. So we know that Fermi liquids have relevant deformations, which should drive under RG to something new in the IR, which in many cases is believed to be a new, genuine interacting fixed point with non-trivial critical exponents. So just to stress how hard a problem this is, I've kind of illustrated here critical systems with lower and lower amounts of symmetries. So first we have, of course, interacting CFTs. So in this case, we've had for a long time perturbative constructions since Wilson-Fisher, but we also have many, many non-perturbative methods, which all of you are experts in, which have allowed, analytic and numerical bootstrap and to do incredible things like classify the space of theories and so on. So if we take one step maybe towards kind of reducing symmetries in some sense, non-relativistic CFTs, you could consider non-relativistic CFTs. So those have Galilean invariance, and time and space aren't related by Lorentz anymore. There's a dynamic critical exponent Z that relates frequency and momentum equal to 2. But there it turns out that there's still enough symmetries to do a lot of similar things. So perturbative constructions also exist. The critical dimension is a bit different, but otherwise it's pretty similar. And it turns out that there's still, a notion of OP, some kind of operator state correspondence, and so on. But if we generalize one step further and allow this dynamic critical exponent Z to be an arbitrary number, there already we don't have much of a handle on these problems. As far as I know, most work is from kind of bottom-up holography, where you can construct such critical phases of matter. And maybe there's some free theories, but yeah, that's basically all we have. And non-Fermi liquids, in a sense, are even more complicated because there's this, Another exponent that, so it's well, let me not define it actually. I shouldn't have put it. Yeah, yep. Sorry, say again. Say, I didn't understand. For the Lifshitz fixed points. Yeah, okay, no, that's, yeah. But there's much less work, I guess, that it's fair to say then, yeah. And non-Fermi liquids are even more complicated because of this, large amount of gapless stuff. So and their even perturbative constructions are quite difficult. So we have some kind of d minus epsilon type approaches, but they all have some nasty features. Either they're non-local, or they break important symmetries like charge conservation or momentum conservation, which you certainly care about. Some have UVIR mixing, which suggests that something's going wrong with the way RG is organized. There's also some very interesting large N approaches to Fermi liquids, but they come with their own subtleties. It's not obvious whether the low energy limit and the large N limits commute. And so you always have to be very careful to make sure you're actually, you don't take the large N limit too fast, so that you're actually accessing the lowest energy dynamics. So, and non-perturbative methods, there's some ideas recently that I'll talk a bit about, but our hope is to kind of help the situation and add new both perturbative and non-perturbative methods. Okay, but going back, so we want to understand non-Fermi liquids, but following the wise advice of Phil Anderson, who in the context of non-Fermi liquids told us to know the enemy being Fermi liquids, I'm going to study Fermi liquids because I'd like to argue that a lot of our difficulties in understanding non-Fermi liquids comes from a poor method to describe Fermi liquids. So more specifically, we don't really have a useful effective field theory of Fermi liquids. And that's what I'm going to try to do. So what do I mean by effective field theory? I think probably most people here know what an effective field theory is. But the idea of effective field theory is to parameterize your ignorance about the microscopics into hopefully a small number of parameters that that aren't too large, so that you still have you can make predictions about the low energy dynamics. And an example where effective field theory is extremely powerful is in spontaneous symmetry breaking, for example, in pions or in condensed matter spin waves and ferromagnets, where the word alone, spontaneous symmetry breaking, tells you what the degree of freedom should be by Goldstone's theorem, and then symmetries tell you how to write down an action for that. So to leading order, you'll have this type of nonlinear sigma model action. But of course, the spirit of effective field theory is to write down all terms that are consistent with symmetries, and typically in a gradient expansion. Okay, so you can have West-Zumino-Witten-like terms or higher derivative terms and so on. And they all come with unknown coefficients that the effective field theory doesn't predict. But the nice thing is that it can compute essentially any observable up to a few unknown coefficients. Good. So, okay, so what kind of effective field theory should we have for Fermi liquids? The first thing you might come up with is just to write a theory of fermions, right? You certainly need fermions for Fermi liquids. Well, actually, that's not so obvious, but that might be the first thing you try. And in fact, it has been done in the 90s. So in this beautiful work. And basically what they did, so in Shankar and Polchinski, is write down some. So first we have a theory of kind of free fermions with some dispersion relation that we're going to put at finite density, and then they write down the most general interaction. Okay, and it's in momentum space because really, your fermion, your low energy degrees of freedom are at finite momentum, at large momentum. And what this work showed beautifully is that out of all these possible couplings, this function of 4 parameters, only a kind of small subset of these are marginal or marginally relevant. And these correspond to Landau parameters and the BCS, the BCS couplings that are responsible for the instability towards spontaneous symmetry breaking, towards the superconducting state. So here it's, is it an interaction you said? So for example, if you had, Dirac fermions, it would be like P minus mu minus chemical potential, or for a non-relativistic fermion, it would be P squared over 2m minus mu. But you could be a bit more general and just say it's an arbitrary function of, and where it's equal to 0 is where you have the Fermi surface. Yeah. Right. So I think, yeah, what this work has done is really elevated Landau's theory of Fermi liquids to to the kind of rigorous standards of Wilsonian RG. And we understand that Fermi liquids are stable because they have mostly marginal corrections, otherwise they're irrelevant, except for one marginally relevant correction. But there's many issues, there's many drawbacks. Was there a question? No, many drawbacks to this approach. One of them is that you kind of have to work in momentum space, which is a bit unusual from the perspective of effective field theory. But a more pragmatic one is that if you actually do perturbation theory with this action, you'll see that there are many subtle cancellations in fermion loops. In any, so more than 1 + 1, but any dimension. Yeah. There are many subtle cancellations, so that it's even hard to guess how correlation functions scale because you don't know how many cancellations there will be. Actually, the statement that there are cancellations is true also in 1 + 1. It's even more true. Yeah, I'll talk about 1 + 1 as well, but I'm mostly interested in the higher dimensions. So fortunately, there is an alternative called bosonization, which kind of was developed around the same time. So I'll tell you how this works. But one issue with these works is that so you kind of represent these degrees of freedom in terms of bosons, in terms of collective bosons, which are particle hole pairs. But it wasn't really known. So what these people came up with is essentially a Gaussian action, and it wasn't known how to capture nonlinearities in this action. So our work is the point of our work is to kind of find the nonlinear completion of this bosonized action to get a systematic effective field theory. And the general strategy will be to write down an effective field theory directly for the shape of the Fermi surface. Okay, so that's the kind of general idea. Yeah. Say again, if it's not in one dimension.
It's not work in one dimension, it's very well known in your.
Yeah, so in 1D, it's very well known how to capture nonlinearities. That's right. But in higher dimensions, so there's some, yeah, that's true.
So what is the statement?
In higher dimensions, it wasn't known. It's not known, or it wasn't known until our work. Yeah, I'll talk about these. Yeah. Yeah. Keep track of it. I think so. So yeah, it's a good question. Come back to it at some point. I don't have a definitive answer, but I think it might keep track of it well. No, actually, I think there's definitely an important role. So I'll come back to this point. Okay, so for the rest of the talk, I'll first kind of argue for why bosonization is useful, and I'll actually use 1 + 1 dimension as a illustrating example, and I'll talk about some of the things you mentioned. Then I'll explain how we can actually get our effective field theory from some tool called coadjoint orbits, but that's not too important. So I'll show you how we get this action. And then finally, we'll use it. So I'll show you how you can use it both for Fermi liquids to understand systematic corrections to Fermi liquids, go beyond Landau's theory of Fermi liquids, understand what, really make Fermi liquids a true effective field theory. What are all the power law corrections to Fermi liquids? And I'll say a few words about going beyond Fermi liquids. Okay, so first bosonization. So let me actually for this part be in 1 + 1 dimension and remind you how bosonization works there. There, it's a really powerful tool that can actually be used to solve exactly some quantum field theories. And I'll look at an extremely simple example, which is the free Dirac fermion, which is dual to a free compact scalar. Okay, so here both sides are free. So you might say, well, both descriptions seem equally useful. But I want to argue that even there, the bosonic description has some advantages. So let's see how this arises. Let's look at the density operator in this theory. So in the fermion language, it's a fermion bilinear. Whereas on the boson side, it's going to be linear in the boson field. And this is what's going to lead to some simplifications. So now let's say we want to compute correlation functions of this current or this density. So on the fermion picture, we'd have to compute this loop, okay? Whereas on the boson side, it's just a tree-level diagram, right? And our theory is Gaussian, and we can basically evaluate this diagram by hand. It's going to be 1/p², and then there's going to be a wave vector squared on top because of this. So it's so simple that we can just evaluate it. Whereas here you'd have to compute this loop, and you would also get that answer. So already here we see that there's a minor advantage on the boson side, but it becomes much more drastic when we go to higher point functions. So what is the connected 13-point function of the density? Well, on the fermion side, you'd have to compute this loop with 13 insertions, and then you'd have to symmetrize over insertions. Even for free fermions, it's not an easy calculation. Whereas on the boson side, it's immediately obvious that all connected higher point functions vanish because the density is just linear in phi and you have a Gaussian theory, okay? And so it turns out that if you do this calculation in the fermion picture after symmetrization, if you do things correctly, you'll find that indeed it vanishes, and this was found here. So here, this was just in a free theory, but the advantage of the boson side persists when I want to couple the system to other things. So for example, if I couple it to a gauge field, and this is the Schwinger model, it can allow us to solve this theory. So on the fermion side, I have some interaction. It's a relevant interaction, and so if you're used to higher dimensions, you would probably say, okay, there's no chance of saying anything. It's just going to flow to something, and I have no perturbative control. There's no large number in the game. Whereas on the boson side, this interaction, so phi shifts under the U1 symmetry. So this is what the interaction looks like. The entire theory is Gaussian. Okay, and so you can trivially solve it. You can go, to unitary gauge, for example, and you'll just see that you get a mass equal to charge for the photon. Okay, so there's really an advantage to this bosonic side. This was one dimension. In higher dimensions, things are not as simple. So you don't have these exact bosonization maps, but there's still a kind of remnant of these. And by the way, the fact that this Schwinger model is solvable on the left-hand side, you can understand as coming from the fact that these loops all cancel for more than 2 insertions. So these cancellations in fermion loops generically don't happen in higher dimensions, but there's still a remnant in the form of approximate loop cancellation. So if you compute a 3-point function, say of the density or the current in higher dimensions, there will be a leading cancellation, and then the subleading answer will. And this is very hard to see from the fermionic. It's very hard to kind of guess from the fermionic description. And these cancellations have made perturbative analysis of non-Fermi liquids fairly difficult, where you want to compute these loops. So what our approach does is to kind of capture these things in a much more transparent way. So in the same way that in 1+1D, the cancellation of higher point functions came from the fact that the boson description was Gaussian. Here, the small remainder you get post approximate cancellation of loops will come from weak, meaning irrelevant interactions in the bosonic picture. And so there's going to be generally speaking, two sources of interaction. One will just come from if the dispersion relation of the fermions is not relativistic. So I showed you a Dirac fermion in the beginning. This arises even in 1+1 dimension. This is what was mentioned by Kay. So if you don't have a Dirac fermion, the boson side has some interactions, and this was already well understood. But there's another source of nonlinearities, which really is inevitable in higher dimensions and comes from the geometry of the Fermi surface, more specifically the curvature of the Fermi surface. And so what our approach does is capture these interactions in the bosonic picture. Yeah.
Is there a way to couple the dimensions to which then will
Well, if you have a flat Fermi surface with with linearly dispersing fermions, then that would do it. Yeah. But otherwise, no. I mean, you could try tuning these two things to cancel each other, but that would be very shape specific and so on. Okay. Any questions so far? All right, so let's see how we actually build this effective field theory. So as I mentioned, what we're going to try to do is build an effective field theory for the shape of the Fermi surface, okay? Which you can think of as this function f of t, x, and p, which depends both on momentum, that describes the shape, and space, because in the semi-classical picture, it also depends on space. Yeah. Yeah. In 2D, you're saying, yeah, in 1+1D, if you had. Mm-hmm. So no, actually, well, even there's this map, right? So there's a more complete version of the bosonization map, where you can map even an interacting fermion to And I think, let's see, so there's a cosine, but the cosine is if you put a mass. I think if you just put the interaction, okay, I don't exactly remember how the map works, but it's known what it maps to. I think it could be that the 4 Fermi term actually is still free on the boson side. You change the radius. Yeah, exactly. I think that's right. Yeah. But putting a mass makes it, yeah. And by the way, putting a mass changes the dispersion relation. And so we expected it to introduce nonlinearities. The filling number is large, you said? Not really. So the lattice won't really play a role in what I'm saying, meaning I'm going to ignore it. So there's no filling. There's a density, which is dimensionful. So filling you're defining as density times lattice constant squared. Yeah, so lattice there's no lattice. I'm going to ignore the lattice. There's just density, which is a dimensionful thing. And this is an effective field theory. It's kind of like, you know, the Gabriel's effective field theory. It's an effective field theory for energies below that scale, the scale set by density. But it's a dimensionful number density. The volume of space of the Fermi surface. Yeah, so that's the total charge. So locally, you know, this thing at every point there's a Fermi surface. That thing's not fixed because you can have charges coming from left and right. But the total, if I integrate this over x and p, that is fixed. That's equal to the total charge of the system. The total charge should be large. The total number of electrons should be large. Yeah. The total. No. Yeah. So I don't want 4 electrons in my experiment. I have a finite density, and I'm taking the thermodynamic limits. Yeah. Thanks for the question. Any other? Yeah. For drawings, yeah, but it doesn't really. I mean, it could be any. Yeah. Yeah. Here, yeah. Let's say they're 2-dimensional. Yeah. Yeah. Well, you know, what is quantum and what is not quantum? So in, for example, 1 + 1D bosonization shows that loops map to not loops, right? So yeah, it's not a duality frame invariant statement. But what we'll do, we'll at the very least recover everything that Shankar-Polchinski did and add more. And you know, the fact that there's a semi-classical picture is really because there's this finite KF. So KF will play the role of the cutoff of the effective field theory. So it's really going to be a kind of controlled expansion and energy scale over KF. Okay, any other questions? So we're interested in writing down an effective field theory for these functions, but they're not just arbitrary functions. It's a kind of subclass of possible functions that are equal to 1 and 0. Okay, they're equal to 1 if the state is occupied, if my momentum is in the Fermi surface, and 0 otherwise. So the goal here is to get an action for the subclass of functions. Okay, so just as a warm-up, let's start with free fermions, with a free Fermi gas. Okay, and later we'll generalize to the interacting case. So free fermions, we actually already know what the equation of motion should be for the distribution function. It's just, again, the collisionless Boltzmann equation. So if I have a Hamiltonian, a kind of single particle Hamiltonian, I can even generalize and consider a potential, an external potential. This is what the equation of motion for this for our degree of freedom that we care about would be. Okay, it's just the collisionless Boltzmann equation. So here, the name of the game is just to find an action that produces this as an equation of motion. Yeah. Yes. Yeah. That's right. F is discontinuous. In fact, let's think about which F's were. So I said it was a subclass of function. Let's think a little more closely about which F's can be reached. So let's just imagine that we start from some kind of seed state, which is a Fermi surface at rest, equal to you know, a kind of isotropic, just a disk and independent of space. And let's think of what possible F's we can get through Hamiltonian evolution. Okay, So I can write this equation schematically like this, make it look like the Schrödinger equation. In fact, this commutator is really just the Poisson bracket of these two functions. Okay. And so you can formally integrate it by just exponentiating this commutator and starting from some seed states. Okay. So the possible f's we can reach, we can see here, are basically the orbit of the seed state under some group. Okay. And this is a group G whose commutators are the Poisson brackets. This is the group of canonical transformations. Okay. And so this orbit is what's called a coadjoint orbit, because strictly speaking, this F0 lives in the coadjoint space. But basically, so this is our kind of manifold of degrees of freedom. Okay, the orbit of some seed state under this group. And it doesn't really matter what seed state you choose, as long as you keep the total charge fixed. So that's Luttinger's theorem. Because of Liouville's theorem of Poisson brackets, you're going to keep the area in phase space fixed. And so that you won't change the total charge of your system by doing this. Yep.
What do you say? You can say group, but I only see one edge, so it's the
Yeah. So here, no. So h is some arbitrary function of x and p. Yeah. Here I'm just kind of imagining. I'm kind of okay. I'm an experimentalist who has complete control over my Hamiltonian. And I want to see what possible states I can reach. So I'm imagining I have an arbitrary function of x and p as h. So the group is the group is all functions of x and p with commutation relations equal to Poisson brackets. Yes. Yeah. Yeah. So here x and p are just let's say vectors in two-dimensional vectors. And yeah. Okay, so that's our degree of freedom. So we can express our degree of freedom either, we can use this to express our degree of freedom instead of f as some group elements that rotated us from some seed states. Let's choose the same seed state. So we could parameterize it with some u, like in pion physics, or even with an element of the algebra, phi. Okay, that looks like this. So here again, phi is an arbitrary element of the algebra, so it depends on x and p. But it turns out that not all phis are independent, because two u's that differ by some group element that leaves my seed state invariant, this will just commute and you'll get the same f. Okay, so really our degree of freedom lives in a quotient space, which is the group of canonical transformations mod the group that of functions of x and p that commute with f0 with the seed states. And it turns out that you can use this kind of gauge redundancy to fix part of phi so that it's no longer an arbitrary function of x and p, but just a function of x and theta, where theta is the angle along your Fermi surface. Okay, so here we see that our degree of freedom will be a boson that depends on space and also time later on at every angle of the Fermi surface. Yeah, that's right. So it would look a little different. I mean, you could do this for disconnected Fermi surfaces, but you'd have an extra label of the disconnected component. Okay, so now we want to write down an action for this phi or this u, or equivalently the f, and we'll just use the EFT approach of writing anything that's possible by anything that's possible in a gradient expansion. And most terms won't surprise you. There's just one term that's that you might not have guessed immediately, because so it's a kind of Wessumino-Witten-like term. It's linear in time derivative. This is what it looks like. And what's surprising about it is that it looks like it depends on my seed state and or equivalently the group elements that took me from my seed state to the actual state f. Whereas this shouldn't matter, right? The physics should not care about what seed state I use. That's just some kind of part of the construction. It should only depend on f. And in fact, the equation of motion, the kinetic equation, just depends on f. But it turns out that the variations of this action indeed only depend on f. Okay. Good. And other than that, we can write down any term that just depends on f. Okay, so that it's indeed not kind of gauge. So that it's not ambiguous. And the first term I'll write down is just a linear term in f that looks like this. Okay, but there's of course more terms. And already just with these two terms, if you compute the equation of motion of this action, it turns out that you get precisely the collisionless Boltzmann equation. Okay, so this is what a free Fermi gas looks like in this language. So there's this non-obvious term which is necessary to get, you know, the collisionless Boltzmann equation. Otherwise, you wouldn't have a time derivative.
So I mentioned like university EU, you know, the algebra group, but always, what does it mean by a conjugated, right?
Yeah, so more strictly, this is a product of F0 is a coadjoint element, and this is an element of the adjoint. So it's a product between coadjoint and adjoint, and yeah, that's what I mean by the trace. Maybe to give you a bit of intuition for this, this is the same term you would have in a ferromagnet that's linear in time derivatives. It's a slightly weird way of writing it in that case, but this is essentially the same physics there, or the same math, I guess. Okay, so this is how you get a free Fermi gas. But now, from the CFT perspective, it's trivial to generalize. We're just going to add any term that is a function of f, and so I'm going to expand in fields and in gradients in a local way. Okay, so here these coefficients. So instead of having Wilsonian coefficients, I kind of have Wilsonian functions of p, but I'm still writing down a local effective field theory because, as usual, the assumption is that I kept all the gapless degrees of freedom. There's nothing long range left other than my degree of freedom. So here, okay, so there's going to be higher order terms. There will also be higher gradient terms and so on. And it turns out that this first correction here precisely produces the well-known Landau parameters. Okay, good. So to ask about suppression, you need to expand for fluctuations. And we'll see that interactions are irrelevant. But so far, it's yeah. Oh, good. Yeah. So probably I want to write delta f. F minus some. So yeah. 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 Yeah, that's right. So that's why. So here in this action, there's no reason that this is less suppressed than this. So actually, when we'll use it, we're going to study fluctuations around some states. That's what you do in practice, right? You're interested in some Fermi surface and you want fluctuations around there. So we'll have F0 plus delta F. I'll put F0 plus delta F, and really what I mean by this is delta F. So I can repackage, what the coefficients mean. So yeah, probably what I really mean is delta F here for it to be useful.
Specific functional form
yeah, so you won't even need RG. That's what's nice here. So this F2 here, it's an arbitrary function of P1, P2. Let's put in rotation invariance. Okay, so then it's going to be a function of whatever, P1 squared, P2 squared, and the angle. This delta F, as you noticed, is going to be a delta function localized on the Fermi surface. So all that's going to be left is a function of the difference between the two angles. And that's precisely the Landau parameters. You could Fourier transform the angle into harmonics, and that's the F0, F1, F2 of Landau parameters that are measured in helium-3. So here we see that we have not only Landau parameters, but kind of a whole tower of generalizations of Landau parameters, which will give irrelevant corrections to Fermi liquids, and which are equally measurable, maybe a little more difficult, but can be studied. No, it's an effective field theory, right? So it's not an exact. It's an expansion in. It's eventually going to be an expansion in energy divided by kf, or momentum divided by kf. So it's a kind of, it's the same way that the pion Lagrangian isn't exactly QCD. It's a lower energy approximation to QCD. Well, you could get better and better, but if you're asking me about what happens in this correlation function when frequency is equal to the Fermi energy, there's no you lose perturbative control, because basically we'll see this when we study fluctuations, but these terms give more and more corrections that are like energy divided by say EF, the Fermi, or KF to some power, and so you just lose perturbative control when you push the energies to those scales.
One way I could think of deriving is that I'm trying to build a basis with the complex and expansion and momentum. But n nodes and the spherical n each of these two coordinates, and then whenever I see something which depends on the momentum, I forget that also depends on the space.
Yeah, so I mean, we'll see that it's a controlled expansion. So once we expand for fluctuations, the corrections are small, as long as you. But there's no way to generically have control, and that's just the statement that many things can become Fermi liquids, right? The UV completion of a Fermi liquid isn't just free fermion. It could be a CFT, it could be a lattice, it could be many things. So you're not going to be able to, derive the UV just from this effective field theory, and you shouldn't. Yep. How can you get FT? Yeah. How do you get this? So this is a Wilsonian coefficient. So it's in effective field theory, there's coefficients that you don't know. And which, okay, you might say, it sucks, but actually the hope is that there's not too many of them. So here it's an infinite tower, which is not great, but still, it's the claim is that any observable you're interested in computing, there's a limited number of coefficients that that will enter in that computation. And in this effective field theory, you can compute anything. Okay, you can compute the 13-point function of current, and it's the same coefficients that will, to some order of precision, will matter. Yeah, so you could try to get a microscopic calculation of these coefficients in some weakly coupled fermion. So for free fermions, all these F2, F3, F4 are 0 for free Fermi gas. And if it's weakly interacting, you could indeed do some kind of kinetic theory calculation and do some matching to figure out what these coefficients are. And generically, they're all going to be activated. There's not, I wouldn't say there's one phenomena that's related to one of them. They're kind of all, unless there's some symmetry reason, they're all non-zero. And and so you might know, there's some bounds, there's some conditions on the first guys, the Landau parameters, to have stability. So that's true, but the others probably are less restricted.
So you'll be able to match them as functions of P1 and P2?
Of the angle, yeah. So I think you can do that. It's not necessarily an easy calculation. In principle, you could do it. Ultimately, when we look at fluctuations, we're going to be localized on the Fermi surface. So it's just going to be a function of angles, difference of angles. So this one is just a function of one angle, this one of two angles. So it's not that bad. Okay, so let's actually try to use it, and we'll start by studying fluctuations. So if we take this action here and expand in phi, okay. So I'm going to choose some seed state, some seed state, which is just a rotation invariant Fermi surface for simplicity, but you could do anything. And I'm going to expand in phi. Okay, so I'm just going to use basically the commutation relations in my algebra, use Poisson brackets to expand F in this action. And what you get to leading order is a Gaussian theory that looks like this. So here I'm in 2+1 dimensions. It depends also on the angle theta. We got localized to the Fermi surface because F0 is a step function. So its derivatives are delta functions. And basically what it looks like is at every angle theta, it looks like a chiral boson that goes here n hat is a unit vector perpendicular to the Fermi surface. So at every angle theta, it looks like a chiral boson that's going away from the Fermi surface. And this, in fact, this linear and time derivative action is what you get in 1+1d for a chiral boson. So and this form of the action is the one that was long known, but we recover it here to leading order. So already here you can do a few nice things. So you can compute the density operator. Similar to our 1+1d example, it's linear in the boson to leading order. But there's this integral over angles, okay? The total density is, in some sense, you can vaguely think of it as the sum of the densities at every theta. And so with this, we can compute, for example, the 2-point function of density. And this is just going to be a tree level diagram, okay, in this picture. But there's still one integral left, which is this integral over theta, okay? And so this is what the thing looks like. This is the propagator of the scalar. And what you get, so this integral over theta allows you to get this non-analyticity, which, even though it's a tree level diagram, which gives the particle hole continuum, the low energy part of the particle hole continuum. So this is something that in the fermion picture, you would have had to do a loop. It would have been an integral over d omega, d2 and 2 momenta. Here we see that there's no loop, but there's still one integral left, which is just an integral over these angles. So in some sense, it's as if we had kind of integrated out the frequency and the radial momentum of the fermions from the start, and kind of resummed it, and all that's left is the radial integral over the soft modes.
In what state are you computing this?
So here it's in the my seed state F0 is just a step function that's rotation. So that's just a disk. So it's a spherical Fermi surface. Fluctuations around a spherical Fermi surface. In general, I think, I mean, at the quadratic level, it probably would look the same, except VF would depend on theta if you had if you didn't have rotation invariance. So yeah, you could do this for any shape, but I'm gonna show it for the simplest case. Okay. So, this is from the quadratic action, but what our construction allows us to do is to go beyond to find nonlinear terms, right? And we're expanding this algebra. We're going to get higher and higher nonlinear terms. So here, let me just show you what the cubic part of the action looks like. So this was our quadratic action. The cubic part, interestingly, starts to couple different patches. Okay, there's derivatives with respect to theta of phi. Here in this quadratic part, we just had a bunch of decoupled kind of chiral bosons, but we see that this picture in some sense breaks down by interactions. So interactions couple different patches. Okay, and so here, so you can do this to any order you like. In particular, with this cubic action, one thing you can compute is the 3-point function of density. And as I advertised before, one thing that's nice is that so this directly gives you the answer, and it's kind of post cancellations. So these interactions are irrelevant, and so you can, in fact, if you just want to get the total the kind of scaling of higher point density, just guess it by looking at the action. Yeah. Okay. Good. Yeah. So in 2D, in 1 + 1D, this would be 0. But these things could exist. Well, sorry, this one. Yeah. Here I probably forgot. There's a d-1. Okay. Yeah. This is in 2 + 1 dimension, but in general dimension, there's a d-1 in front of this term, and this nonlinearity is one that exists in 1 + 1D. But yeah, exactly. In 1 + 1D, the only nonlinearity would be this one. And notice that it has a bit, it's not really coupling different patches. It has a different structure. Here, this nonlinear term coming from the Wessumino-Witten term is this inevitable cubic interaction coming from the geometry of the Fermi surface. And it's suppressed by 1 over PF. More precisely, if I had done an arbitrary shape, it would have been 1 over the curvature, the radius of curvature of the Fermi surface. So it's really that's causing these interesting nonlinearities. So there's some kind of nonlinear structure that's universal and some that's less universal and depends on the Wilsonian coefficients. But this one ends up doing more interesting things precisely because it couples patches, actually. Okay, so that's one thing we can do. So here, as I said, the scaling of endpoint functions is manifest. You see everything post cancellation, and you can actually compute it. So actually, this calculation in the free Fermion language is a 70-page paper from I think the 90s or 2000, no, maybe from 10 or 20 years ago. Whereas here it's a much easier calculation once you have, well, I think our whole paper is probably less than 70 pages, and this is only part of it. Okay, so that's one thing we can do. Another thing we can do with this nonlinear action is go beyond a recent very interesting proposal by Els, Thorngren, and Sentel about an emergent anomaly that Fermi liquids have, and possibly also some passive non-Fermi liquids. So what their proposal is that systems like Fermi liquids have an emergent anomaly, and which in 2 + 1 dimension looks like the 4D chiral anomaly. Okay, so in particular, there's some kind of U1 symmetry at every angle theta. Naively, you can think of it as the fact that density at every angle is conserved. Okay, this is certainly the case in our Gaussian Fermi liquid where every angle is decoupled. But not only that, it also has an anomaly with some non-trivial coefficients. And you can think of this, and in particular, the background gauge field for this anomaly. So the things depend on space-time and theta here. The part that doesn't depend on theta is just the regular U1 symmetry, okay? But the theta dependence is an emergent symmetry, and so you can't control what your background field is. It's not a symmetry you have microscopically. And in particular, an important thing in their statement is that the theta dependence is just kf of theta. Okay, that's how this equation knows about the Fermi surface. And it's easy to see that this is what's necessary to guarantee the fact that if you take your Fermi liquid and your electric field, you're going to start, depopulating charges over here, putting them there in a way that's precisely consistent with this anomaly. So you have an electric field here, and then you put this kf of theta here. So this proposal is really cool because we know anomalies are extremely useful in more vacuum QFT type settings, and it could, in this context, it might be a non-perturbative tool to study non-Fermi liquids if we think this anomaly survives in these more general phases of matter. And in fact, I should say that this kind of inspired our work. One of the first things we wanted to do is just build an effective build a quantum field theory that has this anomaly, and that's exactly what this Gaussian bosonized theory does. It precisely realizes that anomaly. But there's two clues that suggest already in this equation that it's kind of part of a bigger story. The first is that this KF, which we're kind of taking as a background field here, really is a dynamical object, right? In some sense, it's the same thing as the density. If you start having a lot of particle hole pairs, you build the density at some angle, you're going to change KF. Okay, so it's the thing that's on the right hand side here is really some kind of some expectation value of a dynamical field rather than a background field. And in fact, it's roughly the same field that we have on the left hand side. And another thing that might make you uneasy is that one of these, in this 4D chiral anomaly, one of the components is in momentum space. Again, we know that phase space has a different structure than just regular space. And so what we find is that actually this equation is really a linearization of a kind of non-abelian word identity in phase space. So okay, our system has a U1 symmetry, and you can gauge it. And in our construction, you can have gauge fields that depend both on X and P. So it's a kind of continuity relation in phase space. Okay, it's just the statement that probability is conserved in phase space. And this is what the word identity looks like. Okay, where this commutator is the Poisson bracket of these objects. And so now if you linearize this, in particular, you say that the current density has some finite expectation value that depends, that might depend on theta, you'll land on this equation. But there's some kind of nonlinear structure to it, which even Fermi liquid theory knows about. And in particular, one important thing is that the momentum components of this current are in general zero operators. So if you integrate over all of space, you don't just get a conserved charge in general in this general nonlinear description. Yep.
Thanks for that very clear explanation. Another thing you just mentioned in the previous slide was theta fields at different points of coupling.
Yes. Yeah.
This is the issue we're discussing at length today.
Yes, absolutely. Yeah. Yeah.
So now recent work on computing conductivity
Mhm.
is also there.
Mhm.
We find that the coupling is extremely crucial.
Yeah. Yeah. No, I read this paper with the diffusion along the Fermi sphere. I think that's right. Yeah, that's right. So here, this is just a way to get this word identity. But I think it might have more meaning than that. So you could try to, okay, there's certainly an equation that's true, which is just something like this, okay? If this is useful as a quantum field theory, so here I is I wasn't very clear, but I runs over everything, T, X, and P, okay? Usually, we would call this a continuity relation or a conservation law if it just ran over T and X, because then you could integrate over space and you would get a conserved charge. But in general, we see that if you have these kind of nonlinear terms, the P components are non-zero, so there's a right-hand side to the conservation law. But still, there's some structure to it, which is kind of a non-linearization of this thing. There's some operator here, which is not just arbitrary, and you can potentially learn something. Okay. So and in the last few minutes, I'll say a few words about trying to go beyond Fermi liquids. So part of this is still work in progress, but I'll tell you about our hopes. So certainly one thing that you can do is just take this theory, and so the way one usually gets a non-Fermi liquid is one couples a Fermi surface to a gapless boson. This could be a gauge field, or it could be a boson whose mass you fine-tunes to zero. And it's easy to see that this induces a relevant interaction, at least in the Fermi description. So here we can do exactly the same thing. I'm going to do a kind of simplified version of this where I couple a boson whose mass I set to zero to the density, which to leading order is just this. So here I'm just writing it in the Gaussian approximation. Okay, so I have, there's going to be nonlinear corrections to this. But what we see is already in this leading approximation, so usually this would be a Yukawa interaction, right, between the fermions and the boson, and you'd have to compute loops. But here at tree level, we already get, tree level kind of already resums a class of diagrams in the fermion description. And in particular, you can find you can recover a known result for the critical boson 2-point function. So it has this Landau damping coming from the density 2-point function, which gives you this z equals 3 critical exponent. So this kind of recovers an approximation called the RPA approximation to Fermi liquids, and we just get it at tree level. So this is kind of nice because we're kind of starting from something that's we think is close to the right answer, and now we're going to add perturbations to it. And you can also compute the specific heat of this model, and it has this non-Fermi liquid form. Instead of, for Fermi liquids, this would just be linear in T. But of course, this is not the end of the story. There are nonlinearities. In the case of Fermi liquids, these nonlinearities are irrelevant. They had more gradients, and they were suppressed by 1 over PF. But here, it's not obvious that's the case. Yeah, question.
You were saying it's easy to say it's relevant.
Yeah, so I didn't say that yet. Oh, in the fermion description? In this description, it's not that easy. Well, I didn't tell you how to see it. Yeah. If I didn't, yeah, just for the Fermi liquid, here it's easy to see it's irrelevant, that these cubic terms are irrelevant, just because, they have an extra gradient and there's a 1 over PF. So as long as K, as long as momentum Q is smaller than PF, you're good. But here, things scale a bit differently, right? Omega scales. So here at small frequencies, we're going to drop this term. We're just going to have omega over Q. And so omega scales like Q cube, kind of to leading order. And in this scaling, it's less obvious that they're irrelevant. And in fact, it's no longer the case. So you can look again at, yeah, okay, I won't explain it beyond that. But you can look again at nonlinearities and update your scaling, and you'll find that they're relevant in the case of interest, 2 + 1 dimensions. In fact, you can find the upper critical dimension, that it's 3, and that's also a well-known fact from the fermion description. But nevertheless, you can kind of recycle all existing perturbative methods in the fermion description into this boson description. So one method that's pretty popular and pretty old is this non-local generalization of it, where you make the boson less soft by changing its kinetic term into something non-local, and this allows you to make d equals 2 the critical dimension. So this is something we can of course do in this action. And this gives you a perturbative approach, albeit it's non-local, to the critical point. And so even in this perturbative setting, we think there's an advantage because you killed a bunch of loops. Okay, we've already resummed a bunch of loops. So diagrams, for example, that look like this. This is a diagram that's somewhat famous in the community. It even has a name. It's a 3-loop diagram in the fermion picture, but here it's just a 1-loop diagram. Okay, the fermion loops have been replaced by 3-point functions of the density, and so on. Moreover, this approach can also give us new perturbative methods. In particular, we think we can directly do a 3 - epsilon expansion that wouldn't require non-localities. And this is very difficult from the fermion picture. And so one target for this work is to figure out if z equals 3 is the true critical scaling dimension, dynamic critical exponent, or if there are corrections to it in non-Fermi liquids. So this is perturbative. And finally, we have some hopes of trying to make also non-perturbative statements. And in this line of work, there's some inspiring papers by these people where they tried to use this anomaly or some version of this anomaly to make statements about non-Fermi liquids. Now that we have a kind of, we understand what's breaking the LU1 symmetry, this might help us understand some aspects of non-Fermi liquids non-perturbatively. But those are mostly hopes for now. Okay, so let me close here. I'd like to make just one comment that kind of ties this to CFTs in some way. So there's one question in CFT, which is, what phase of matter do you get if you take a CFT and you turn on a chemical potential? And I think in this kind of general setup, probably Subir asked it nicely in this paper, but it's also been kind of revived in the context of the large charge business and the effective field theories that Gabriel talked about. But in most of this work, one is assuming that you get a superfluid phase, okay? But there's, condensed matter physicists know many other phases of matter than superfluids. that they find in particular more interesting than superfluids sometimes. And so you could ask which phases can be realized. So can you have, well, a Fermi liquid? Could you have non-Fermi liquid? Could you have other symmetry broken phases? Could you have an extremal black hole? Or could you rule out some of these phases? Like are some of these just kind of cannot be UV completed by CFTs? That would be a very ambitious goal. And in particular, could you kind of find UV-IR constraints on these effective field theories if you add in the assumption that you want it to be UV completed by a CFT? And one step in this direction for the case of superfluids was made in this paper where they kind of were able to find, swampland style bounds in superfluid effective field theories, assuming you get a CFT. So I think there's a lot of interesting open questions here, not necessarily just related to Fermi liquids, but just to kind of finite density physics and its relation to CFT. Okay, I'll stop here and take any questions. Thanks for your attention. Yeah, you started. Yeah, you started talking.
Each step is what's made to zero.
Yeah.
So the other people want I think it's one of the logistically would correspond to register. It's not the same as you said.
Yeah, I mean it's exactly what you said. So in this approach, it's scaling wave vector and frequency to zero. So it's much simpler. And with some ratio of them being fixed, which is not necessarily just z equals 1, depending on what you want to study. But yeah, you're scaling wave vector to zero. So it makes it much easier to, much more straightforward to kind of classify which terms are irrelevant and so on. Yeah, okay, good. So that's definitely, bosonization is not as great if you're interested in the fermion. Sorry?
1D. Yeah,
in 1D you can do anything. In 1 plus 1D. Here, so yeah, there's several. I'm tempted by several different answers to this question. I'm not sure which one is the best. I'll start by saying one thing, which is that you don't always have fermions. You could have Fermi liquids without fermionic operators, without gauge invariant fermionic operators. That's of course just a cop out. But you could also. So I think one point that's very important is that in 1D, in 1 plus 1D, fermionic correlation functions are basically fixed by the bosonic ones in some sense, right? There aren't new parameters there. Whereas I don't think, I don't have a proof of this, but I don't think this should be the case in higher dimensions. So I think there should be freedom for, fermionic correlation functions to be different, to have a smaller, a residue, perhaps even vanishing in a Fermi liquid in a way that's not necessarily tied to these correlation functions. But I agree that that would be an interesting direction to kind of try to generalize and see if fermionic correlation functions should be constrained or not by the. Yeah. This one.
So is the amount of
which parameter? The link. You're talking about this coupling? Oh, F3. Yes, absolutely. Yeah. That's right. So here I did it for the case of Fermi gas. So even for the Fermi gas, doing the fermionic calculation is extremely difficult, and it was this many-page paper. But here it's much easier. But indeed. So for us it's easy. It's not too hard to generalize to Landau parameters, and F2. So the kind of quadratic, the standard Landau parameters enter even in linear response, okay, in a way that's understood, a bit unwieldy, but still well understood. But here, these generalized Landau parameters, F3, that I called F3, will enter in the cubic response and so on. Yes, yeah. The scaling is the same. Yeah, basically, cubic terms, delta F cube roughly is grad phi cube. So they look the same. It's just that they couple different angles, so they make calculations a bit harder. But it really looks the same as this, but with different angles coupled. That's what these higher Landau parameters do. Yep.
So what our friends from the fundamental community like to do, they take the four-point interaction Then there is the other transformed to capital.
Yeah.
Then you have three possibilities, including the superconducting channel. So how does this compare to yours?
Yeah, so there are these derivations of 1 + 1D bosonization, which there are various versions of it, which some of which involve these tricks. I don't know if I think, okay, I guess you could have tried, I think this is what inspired a lot of the early bosonization work also in higher dimensions, things like this. So there's this coherent state approach that is kind of similar, but I think it's probably very hard to kind of generalize and capture all nonlinearities in this approach. Yeah. 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 So. Yeah. Right.
Right. The three choices. That's right. So he would.
Yeah. Sorry. Okay. Right.
Yeah. So this capital phi is a Hubbard field from the Landau parameter. You can think of that. And it's one particular Landau channel that's playing in the table. And there's many possibilities. It could be the BTS channel, it could be some angular momentum channel, which is correspond to power instability. Or it could be a finite momentum channel, which is spin and charge density waves. These are all different instances of this theory.
Yeah.
So this is a key figure. You have that kind of a topic is what you think, right?
Yeah.
We all have.
So one simple generalization is to have something like this, e to the I L theta times. Yeah. So depending on your spin, if you have a spatial spin. Yeah.
Yeah, that's, there's really infinite number of possible stabilities of the liquid, and the microscopic determines which one is most important. And once you know which one it is, then let's make it right. Then there is key.
Oh, thanks. Yes.
So if F3 is on the same footing as F2, is the monarchic and F3?
The lower stuff is, kind of what has to be bigger than something, let's say -1 to avoid instabilities. The higher either derivative or higher order in field corrections usually don't do something too bad, right? Since they're kind of irrelevant corrections. So that's what I was saying. There's no obvious kind of stability bound on F3s. There could be other types of bounds, maybe swampland type bounds on these coefficients. That's not obvious, but yeah.
Any other comment? Question? Well, if not, let's thank Luca again.